I'm Ethan Weber, and this work is called Detecting Natural Disasters, Damage, and Incidents in the Wild. When a natural disaster or incident occurs, such as an earthquake, timely response is crucial and life-saving. However, the process remains labor-intensive with manual intervention. Advancements are being made, including on-the-ground survey tools by UNDP, such as this tool where people can take pictures to better inform response. However, the pipeline is not automated. Related work in computer vision literature shows promising results on using satellite imagery. The recent XView2 challenge introduced a new dataset of satellite images for building damage assessment. Gupta et al. Created this XView2 dataset, which contains a diverse set of satellite images across the world. Now, what about social media? When an incident occurs, such as a flood, many people post on social media. However, it's currently difficult to filter for incidents with text alone or hashtags due to the noise. Furthermore, image-based methods are largely non-existent because on-the-ground incident datasets are scarce and limited in size and diversity. This motivates our work for detecting natural disasters, damage, and incidents in images, where we create a dataset and train a model to filter images in the wild. With a computer vision model like this, a humanitarian response system could look like the following. Here we see a collection of tweets, such as those that may be posted during an incident. Images with incidents are detected, filtering out the noise. By plotting these images by their location with on-the-ground insights, an automatically built damage map can inform how to respond to emergencies effectively. This motivates our work. We present the large-scale incidents dataset. We download many images of incidents from Google Images, and we label these using Amazon Mechanical Turk. In the end, we create a dataset of 43 different incidents and 49 different places, which contain around 450,000 scene-centric images. On the left, we show a breakdown of the class positive images in blue and the class negatives in orange, which we will explain shortly. On the right, we illustrate diversity in our dataset with a 2D histogram of image count for incident and place combination. With our dataset defined, we can create a baseline model. Note that this is a single label multi-class problem, and we use the standard cross-entropy loss. With a ResNet backbone, we attach two fully connected layers that go to an incident category and a place category. Note that with the image shown here, we see a burning house. Because this model uses the cross-entropy loss, it only sees class positive images. On the left, you see an airplane accident, and on the right, you see an on-fire incident. When this model is deployed in the wild, it is overconfident in its predictions. You can see that the model is 100% confident that this is an airplane accident, while on the right, it is 99% confident that this image is on fire. Although this may be true, it is not an incident. Furthermore, for the plane example, although it looks similar to an airplane accident, sharing many similar features, it in fact is an intact airplane. So, to resolve this problem, what we did is we collected around 700,000 class negative images, which is included in our dataset. On the left, you see the airplane accident, and on the right, you see some class negatives that we have collected, which are not airplane accidents. On the left, you see on fire, and on the right, you see not on fire images, which are our class negative images for the category on fire. Here we see some more examples: not airplane accident, not on fire, despite it being fire, not with smoke, despite the condensation in the air, and not flooded, despite the fact that this is a lake. Recall our original model with the cross-entropy loss. It is essentially a classification model where the problem is to classify incidents among many class positives. What we do is we simply modify this to a binary cross-entropy loss, and we treat the problem more like a detection problem among many challenging negatives. In particular, what we do is we introduce a weight vector W to penalize class negatives. Now, whenever we make a prediction, which is high confidence for a class negative, our weight vector can have a 1 in the correct position, which will allow us to penalize this prediction and therefore mitigate false positives when going in the wild. With the dataset collected, we can now perform experiments to figure out which model to use when going in the wild. What we do is we split our dataset into a train, validation, and test set of 90, 10, and 10%. Now, if you notice on the left, this is the results that we get with our original cross-entropy model without our negative loss. You can notice that there are many airplanes that are intact, many fires that are not incidents, and many bikes that are not accidents. When using our negative loss, you'll notice that the images that are predicted with top confidence are much more correct. In fact, when looking at the difference between the baseline model and our final model using the class negative loss, you'll notice an increased average precision in almost all incidents. Furthermore, when looking at incidents in places, when using the class negative loss, we see a boost in our average precision. Now that we have a model trained with class negatives, which performs robustly against false positives, we can go to the wild and perform experiments. In this setting, what we do is we download 40 million geotag Flickr images. On the left, you can see the Flickr images plotted. On the right, you can see some of the diverse images shown. We then filter by earthquakes, in this case, and we plot earthquake epicenters in red. Now what we do is we report the metric accuracy at X kilometers, which is the percent of images that fall within X kilometers of any given epicenter. Notice that when filtering with high confidence for earthquakes, we achieve images that are much closer to the expected location, which is the earthquake epicenters. We repeat this for volcanic eruptions, and notice that the images fall much closer to locations of volcanoes. Here you can see an interface that we've created where you can browse different incidents that we have filtered in Flickr images. This is available on our project site. Now we perform an experiment on Twitter. In this setting, we download many tweets related to specific incidents in the past and filter by a radius. Now what we can do is we can filter by images. Notice on the right, you can see that we have filtered the noisy images on the left down to a clean set of images on the right. We repeat this for many different events for both earthquakes and floods. Here you can see the filter results when plotted. When looking at performance, our filtered case does a much better job compared to the unfiltered keyword-based only approach. We report accuracy based on ground truth collected from Amazon Mechanical Turk. Another experiment that we perform is for incident event detection, where we evaluate our model over a series of tweets collected over time, in this case from August 2017 to August 2018, with many different natural disaster tags, including blizzard, thunderstorm, tornado, and wildfire. In this case, we filter by earthquakes, and we notice that for earthquakes that occur, we see that many earthquake-related tweets based on the image filtering spike right after the events. Looking at more common events, such as floods, tornadoes, thunderstorms, and wildfires, we also perform experiments where we look at the frequency of tweets over the course of the year. Please see code, data, and models available at our project site. Thank you.